run over. But in any case, we're going to release this assignment 1, text retrieval. So you can start working on some of the problems and looking at the software we provided, and to see whether you'll be able to sort of able to implement some of the retrieval models that we talk about in the lecture, and be able to do the proper evaluation as well. So I believe everybody already have studied the probabilistics, some basic probabilistics principles. So I would like to show you a video in YouTube which talk about the importance of probability. Anybody familiar with Monty Hall problem? Okay, yeah, most of them haven't, but for people who know that, maybe just try to remember what it is and how probability can help.
With me, Ron Clark. Imagine you are on a game show. The game show host shows you 3 doors. Behind one of the doors is the star prize, a car. Behind the other 2 doors are booby prizes, 2 goats. You have no way of knowing which door conceals which item, and whichever door you pick, you'll receive the prize behind it. You are asked to pick a door. But before it is opened, the game show host opens one of the other 2 doors. Now the host knows where the car is, and he always opens a door to reveal a goat. You are then asked whether you'd like to swap your chosen door for the one remaining closed door. The question is, should you swap? Should you stick with your original choice? Or does it make no difference what you do? Which would give you the greatest chance of winning the car? I'll give you 10 seconds to think about it. So, what do you think? Now, most people will say that it makes no difference whether you swap or not. Behind one closed door is a goat, and behind the other closed door is the car. Therefore, the chances of choosing the car are 50-50, so it makes no difference whether you swap or not. Now, this sounds perfectly sensible. However, it's not correct. The Monty Hall problem is a puzzle about probability. The problem is simple to understand, but the answer is counterintuitive. So what should you do? The answer is you should always swap, as this gives twice the chance of winning the car. Why? Well, there are many different ways to explain why, but perhaps the easiest is to examine what your chances of winning the car are for the 2 strategies, swapping and not swapping. Let's start by looking at what happens if you choose not to swap. At the start of the game, you are asked to pick a door. Since there are 3 doors and only one hides the car, the probability of you picking the car is 1 in 3, or about 33%. And since there are 2 goats, the probability of you picking a goat is 2 in 3, or about 66%. Now, if you don't swap your door, it doesn't matter which other goat door the host opens, because you are sticking with your first choice, and the chance that you've already picked the car is 33%, and the chance that you've already picked a goat is 66%. So by not swapping, you have a 33% chance of winning the car and a 66% chance of winning a goat. Now, let's look at the consequences of swapping. Let's consider what happens if, by luck, you pick the car first time, a 33% chance. It's obvious that if you pick the car on your first go and then swap, you are going to end up with a goat. So if you swap, you're going to win a goat at least 33% of the time. What about if you pick a goat first time? Well, here is the crux of the problem. This time, there is only one goat the host can reveal. The host opens the only other goat door, and then you swap to the remaining closed door, the car. In fact, every time you pick a goat door first time and then swap, you will win the car. And the chances of you picking a goat first time are 66%. So by swapping, you have a 33% chance of winning a goat by picking the car first time, and a 66% chance of winning the car by picking a goat first time. So, you should always swap to the remaining door. Why? Because if you do, you'll have a 66% chance of winning the car, and only a 33% chance if you don't. And that is double the chance. I hope this explanation makes sense, and that you can see the truth behind the Monty Hall problem. The only remaining question is, do you actually want to win a car? Or would you rather win a goat?
So this is an example to show you how probability works. And so today we're going to talk about is how probability can help us to address information retrieval problem. So before I start, I think it's also very good for me to quickly go through this. So I believe you already have the slides here to go through the basic probability. What I want to highlight here is the Bayesian rule, which we use heavily. In our information retrieval model. So here is an example show how Bayesian rule actually help us to do the prediction. So suppose you experiment with 3 coins here, and then say suppose you have 3 coins, C1, C2, C3, and for each of the coins, you basically do this experiment, flip it for 6 times, and then now after the experiment, you sort of hide without which one is which one, and then you say you observe that someone actually pick up one of the coin and then do the experiment, and then this is a sequence of the flipping coins, and then ask you to guess which coin this guy actually has chosen. So this is you can actually using Bayesian to formulate that problem and try to make your prediction. So what you can do is that here's basically the problem. For each of the class, you have the observation, and then now there's a new observation comes in, and then you want to say classify, say to this category, to these 3 categories, and what usually do is to calculate so-called posterior probability, which is say I have the observation. What is probability that belong to one of the category? And what you can actually do is that you calculate the posterior probability and pick up the class, the coin, which can maximize that posterior probability. In common, in real situation, it's very hard to calculate the posterior probability. What you can do is apply the Bayesian rule. where you can have this apply breeze rule, and then you basically, for each of class, you build a model for that particular class. And then this also has a prime distribution about that particular class. And then based on this too, you can actually calculate the posterior probability. So for the likelihood, because you have, in the beginning, you have done the experiment for each of the class, therefore using this observation to calculate the likelihood function, which actually is the parameter of your model. And so this procedure is called parameter estimation. So which is, in fact, we also use in information retrieval. We also need to build an information retrieval model, which essentially is conduct parameter estimation. And once you have that, let's say the prime probability, you see, you consider, or you assume this three class equally probable, you can do the calculation about this logical function, and then you have the prime probability. Therefore, you can calculate the posterior probability. This is basically how to actually calculate. So Bayes' rule actually help you, instead of do this posterior, you calculate likelihood and prime and get a calculation done. So that's the basic Bayes' rule. I hope you are already familiar with that. So this is outline of what we're going to talk about today. So first, we're going to have some brief introduction about the mathematical model, and then we're going to talk about language model, which has been quite popular in information retrieval field. So the concept of language model is like you construct a language for each of the document, and then you build a model for each of the document. And then you try to generate query such that whether that language will generate the right query, and then calculate the probability, and then using that probability as a score to rank document. And then we're going to talk about relevant model. So the relevant model is the, okay, we need to have assumption about what is relevant. So instead of build this relevant model indirectly, we can actually calculate the relevance directly and coming with a relevant model. And that actually leads to the BN25 formula, which heavily used in practice. And then after that, we're going to talk about portfolio theory of IR. So we started evaluation. We understand the evaluation methodology and evaluation matrix, like position recall, MAP, MDCG, and we understand the significance. So once we have two algorithms, we were able to compare whether which one is better. So remember, you have a PageRank, you have a vector space model, you have TF-IDF. Now today we're going to talk about a language model and relevance model. So I think it's really from the assignment one, and you're able to using the evaluation methodology that we learned to do the proper evaluation. And I think we talk about relevant feedback as well. And Emily also introduced like online learning, which help the system to sort of learn user feedback. And so that is a situation, even though you don't have a relevant even you don't have a rating or don't have a judgment from the user, but using the clicks able to evaluate your model, evaluate your ranking. So today again we're going to focus on relevant matching here. Before I think let's go through some exercise. try to make sure you be able to understand the vector space model we talked about this Wednesday. Still remember what is TF idea? Someone can tell me what is TF idea. It's not a long time ago, right? It's Wednesday, 2 days ago. Someone can tell me about what is TF? Turn frequency. Yeah.
So yeah, TF term frequency, which is the frequency at which a particular term occurs in your corpus. No, in your text.
In the document.
In the document.
In the document.
IDF is the inverse document frequency.
Yeah.
So the document frequency is how often the term, in how many documents a particular term occurs.
Yeah, that's exactly it is. So, why do we need to idea when we try to come in with a greeting function?
It deals with the fact that certain terms are very common, but they might not be very precise. So a term like the or a might occur in many texts, but its meaning it will allow us to select many documents, but it will not allow us to discriminate among topics.
Yeah. So let's talk about discriminative power of the terms. Some terms might be quite it occurs everywhere in the collection. Therefore, if you're using it as a query, then you probably will be able to achieve what you're really looking for. But for some terms that are very specific for a certain topic, therefore you would be easily to using that to find what you really want. So this is a very simple exercise, allow you to familiar yourself with the TF IDF that we have learned, and you can, through this to be able to understand TF IDF and do some calculation. It's not that difficult, and in fact, this is example. This example question that I had for the final written exam, so you could get an idea about what question you kind of expect from the written exam as well. And so for white formulas and then do the calculation and see what result you actually come out with. Just so you have to be able to do the calculation before you ask the computer to do, right? So otherwise, I don't think they will be able to implement that correctly. Anyway, so this is something exercise. Any questions? No. I briefly talked about model last time. So it's a simplified representation of real object, and it is very crucial because it actually helps us to understand, provide insight, answer, the guidance, and hopefully make us make some prediction. And it's an intermediate between data and understanding. And just an example, the fashion model. Everybody know that it's a person which basically employed to display clothes. So it's supposed to understand how you look like if you wear that clothes. But the reality is that for us, we become better, whereas the model becomes thinner. So the split between the reality and the fashion industry is really great. That it doesn't really represent what would look like if you common people wear it. So that the point, what I try to emphasize, the point here is that any model should represent a real object. If there's a difference, there's a huge difference, then you might run into trouble. And so what we have happened here is that we not a fashion model, build a fashion model, but here we build a mathematical model. And another example is finance. In the stock market, people come in with a mathematical model, try to understand how the stock price moves, and hopefully can make some forecast. A simple mathematical equation here is the random walk assumption here. You assume that stock follows random walk. Another interesting example is 2008, the financial crisis. And what happens is that in the financial field, they're using a lot of mathematical models to do the forecasting or do the risk management. And one of particular interesting one is called Gaussian Coppola function, which David Lee actually published 2000 published paper talking about the mathematical formulation, mathematical method, which can actually predict whether this company is likely to default. And people use it. Financial industry, people use it to price, to do this, to estimate whether you would be able to default if you will lend money to you. So this is a whole, we call it credit risk. People using it to to predict or to evaluate your credibility. And unfortunately, what happens in the financial industry, people don't really understand the model at all. The people use it, not really understand the model at all, don't understand the assumption at all, but using it to pricing the assets. Therefore, they have a big consequence, drawback. So some people actually blame that this mathematical model was wrong. But in fact, what I kind of think is really depends on how you can be able to use it. By any mathematical model, it's wrong, right? It's an abstract representation of real world. Therefore, by definition, it's wrong. It really depends on when you use it. You definitely need to know whether in what situation it fits, in what situation it doesn't. And David Lee almost guaranteed to get a Nobel Prize, and because the financial prize 2008, he wasn't able to get, unfortunately. So now back to our information retrieval field, and we build a mathematical as well. Google builds mathematical as well. So what we're going to talk about today is talk about these some basic retrieval models. So we're going to talk about language model and how we can estimate, build a document representation, and then talk about some extension like Bayesian extension, query, document generation. There's another extension, and also we talk about topic model. And previously we talk about the bag of words rather, we haven't considered the dependence between words. The topic model actually helps you to understand that. And after that, we have this link between relevance model and language model. And there's a paper actually talking about how we can actually build a link between these two. So this is a graph illustrate why we need to calculate relevance between user information need and document. So when user coming with the information need and with certain representation, if you remember, the query might be one of the representations. It could be other, like user profile, rating, and so on and so forth. So that's denoted as Q. And then you have a set of documents here. You want to match building a match, matching the query with a document in a collection. The language model does is, so okay, now forget about relevant prediction. Let's construct a document model for each of the document here in the collection. Using to try to understand what this document is about. And then I will say, okay, a considered query can be generated or can be sampled from the document model, and see how likely the query actually generates from that. If the query is very likely to generate that, then that means that document might be relevant. So that's basically the underlying assumption. By doing this, you can get rid of, say, ask the user to provide relevant judgment and so, but focus on the statistics in the document. Do you wanna? If there's some more over there. So in the natural language processing, so language model is not new things in information retrieval. In the natural language processing, people are talking about language model as well. The idea, in fact, is simple. Basically, we're going to assign a probability distribution to a sequence of words. So in this case, you've got T is the terms in the document. Let's say we have n number of terms in the document. And we're going to construct a joint probability of those terms, and which basically use it to capture the language of the document. And once you have that probability, this joint probability, and then you can use that to compute conditional probability. Any conditional probability you want to compute. And therefore, you can actually do the forecasting given the sequence of words that occur now. What would be the next word that would likely to occur? And this is what happens in the natural language processing, speech recognition, and so on and so forth. They build this conditional probability. Whereas in IR, what we are actually doing is that for each document here, we're going to have a language. We're going to have a joint distribution of terms if they occur in the document, and to come in with the language of that particular specific document. And then once you have that, we can actually say, consider this query again as a small piece of text as a document to see how likely this query can generate from this document model. That's the basic idea. So if you construct the document language model, we can somehow generate query from the sentence of the language. Obviously, if the language model is accurate. So here is an example. Let's say if we have a very simple model, what other terms can be generated? Let's say we have five terms, A, B, C, D, E. And we consider them equally probable, and they are all independent. And if you're using that, if you have those assumptions, this is actually the sequence that you've been able to generate, sequence of words you've been able to generate. Obviously, if you change the probability, say, okay, for the term A, the probability going to generate term A would be 0.4. It would be higher than the rest of terms. Therefore, when you generate a sequence, you can see that A would be likely to be there. So that's the idea. And so this stuff has been talked about in Shannon's the seminar work. When he start to sort of form the idea of entropy. So what happens in IR is that we talk about backward words model, right? So we basically get rid of dependency between words. So if you have the original joint distribution given a document, you can factorize into three factors. But if you have assumption about dependency, you will come with different mathematical model. For example, say I have a bigram language model, which basically assume that the term occurs now only dependent on immediate previous terms. So if you have assumption, you have a called bigram model. And you would also be able to have the unigram model, which is basically throw away all the conditional dependency. If you do that, you would get this bag of words model. So by doing this, in fact, you simplify the model, and which has been widely used in information retrieval. Any questions so far? Yeah.
Are we going to have a look later when each of the assumptions are appropriate?
Mm-hmm. You mean add additional layer?
No, if we're going to see some cases where you would make the one assumption but not the other.
Uh-huh.
Because what's there is just probability statements given a certain assumptions. But I wonder if we have an assignment for homework, which assumption would we make? You know, unigram, bigram, how would you decide them?
How would you decide? Right. So what you could using if you look at most of IR model is unigram, and people test it say using bigram, and to test the result and find out the improvement is not that significant.
Yeah, maybe because bigram is too strong of a simplification still. Mm-hmm. So maybe we need to use the full dependency.
It's very hard, given that you have more than millions of documents, and vocabulary obviously also large. So you probably can't use that. But you can build something in between, like people build the Bayesian networks, which I learn the dependency of terms, right? I can then have come in with a graphic model of the terms. And therefore, for some of the terms, there's less dependent. I get rid of that. Some of them they are, dependent. I can do a make use of that. So that's one approach people proposed in the past. Another is talking about topic model, which I'm gonna briefly talk about a topic model, which basically say I have a hidden layer, which is topic, and then using the topic to link to the terms. Some of terms in this topic, some other terms in another topic, and build a probability on top of that. So that's the way to come in with a trackable model where cover dependency. So if you agree, you can try this some of the alternative models in the assignment to see whether how good that is. I think it's a very good question. So whatever model you build up, what you can do for document ranking is, first you established for each document in the collection a document language model, right? So you get given observation, which is words occurring in a given document, and you build is a mathematical model. And from then, second, given a query, we're gonna rank the document on the basis of the probability that how likely this query gonna generate from that particular document model. So, and I said, once you have the mathematical IR model, in fact, you have the assumption of the relevance. So here you can see that we consider that this probability, the likelihood, is interpreted as the likelihood that the document is relevant to the person. So this is basically an assumption there. Otherwise, you wouldn't be able to say, okay, what does this mean? I'm using it to run the document. It's got to be some meaning there, right? So in summary, from document, you get a document model. And from document model, you generate a query. That's it. Very simple. So let's see what would be the simplest calculation we can actually do by applying language model. Okay, so here, let's say you already obtained the document model. You want to generate query. Here we have assumption, which is Unigram language model. Basically, the terms are independent. Therefore, you can factorize this joint probability into consider term are independent. Therefore, you calculate the likelihood of each of the terms occurring in the query, and then multiply them together. And so here the TF is term frequency, and LD is basically the document length. So here it basically means that how likely this term gonna occur in the document. And what I did is using maximum likelihood estimation. So for people not really familiar with maximum likelihood, I think in the the material that I prepared for you, you can actually go through it to understand what do I mean maximum likelihood estimation. So what we can do here is that instead of directly calculate, we apply logarithm transform to that formula. So instead of doing the multiplication, we apply logarithm of the ratio here and sum them up together. So any reason why we need to using log transform when we do the calculation? Perhaps in the first question, even before that, if I apply logarithm transform to this probability, to the logical function, and I've obtained a score for that particular document, is it still valid using that score to rank document? Yeah, people will
It's a monotonic.
Monotonic, yeah. Okay, yeah. So the answer is yes, because log transform is monotonically increased. Therefore, you're able to using logarithm transform. But why we need the logarithm transform here?
Because the frequencies can be really small.
Right?
The frequencies can be really small.
Mm-hmm.
We've done before.
Yeah. So that's correct. So frequency could be very small. Think about the document, it might be very long, right? So if you calculate, in most of the cases it will be 0, 0, 0, 1 perhaps. And you multiply them together, in fact it could be very, very small. And computer will be able to handle that. So in general practice, what you have is using logarithm transform. Any question about that? Still, there's another problem, is the zero probability. What if the term here, TF, term frequency is 0? If you're using log transform, you'll be able to calculate, computer will be able to calculate, right? So it's a log of 0. So the second problem is the raw term frequency is less reliable, right? This term might occur there for one or two times, but actually represents this by this document really talk about that particular topic, but this term might only occur once, 2 times. So what we need to do is that we need to have a smooth estimation. So here's a way to do that. So instead of directly using maximum likelihood estimation, what you can actually have is we're going to have a linear smoothing. So we're going to sense the estimation from the collection statistics. So again, it's the same thing, term frequency in the document divided by length of the document. And I have another term here, is the term frequency in the collection. So this is the collection frequency we talked about in Wednesday, and divided by the length of collection. So what do I mean by length of collection? Basically, you put all the documents, append all the documents together, and calculate how many terms occur there. So this is the length of the collection. You're using lambda, which linearly balance these two estimations. And so this is the model here is called linear smoothed language model, which actually work quite well. Some people actually try to find a reason why it works well, and to show that in fact there's a little bit idea bit. You develop idea bit into the model here. There's a paper about how to sort of formally justify the formula here. So in fact, this is a paper talking about that. So if you're interested, you can look at it. Any questions? Are you sure you're able to implement it? Another smoothing is called Bayesian smoothing. In fact, it's so instead of do the maximum likelihood estimation, I maximize the posterior probability. So if you look at the final formula here is that we got additional parameter, which is alpha. Alpha is used again to balance the collection statistics, which is the TF term frequency in the collection and the length of collection. But instead of using linear balance, I'm using this called so-called derivative distribution as a prime to construct the model and maximize the posterior probability. You get that formula, which using alpha to balance this two. So nice thing about this is that you can consider this the alpha and multiply by the collection frequency as a pseudo count, as a count saying before I observe this document, this is the count that I might have from the collection about that particular document. So you can, in your assignment 1, I think what you can do, you can implement this as well and compare with linear smoothing. Perhaps to change the lambda a bit to see, whether this model will produce better result or not.
How would you usually choose the parameters of a network?
That's a very good question. So, one way is that the simplest way is to we have the track evaluation. We have the track data set, which user provide a judgment already. So what you can do cross-validation, meaning that you say, I have this data, and this is my judgment. I'm gonna run a setup parameter as, in this case, let's say 0.5 this take arbitrary. Let's say alpha equal to 100. I'm gonna see the, let's say, mean average precision using the judgment as the ground truth. And I change my parameter again and see that whether the result would improve or drop. And you can actually draw the curve, right? And pick up the one which is maximum. You know, to do is then you basically learn the parameter. Then this is basically called validation set. You then have additional test set which you can test it against other approach by this optimal parameter you have learned. So that's the basic principle. There's still some problem with the linear smoothing and the Bayesian smoothing. Is that from the mathematical perspective, if you have a given document, a constructed model, in fact you are estimating that particular mathematical model. Therefore, there's any estimation you would like to have, you have uncertainty associated with that estimation. So you might have a certain probability to estimate model like this. You might have a certain probability to estimate model like that. Ideally, you want averaging over all these possible language model together, coming with your calculation. So you're actually coming with that to have the so-called full Bayesian treatment. If people in machine learning would know that, and you know, have some improvement, not significant in fact. The topic model, which you know is related to the question you asked, is that the bag of words assumption. In the vector space model, you know, each document is actually presented in a high-dimensional space where the terms are independent. So in the unigram model or in the linear smoothing and Bayesian smoothing, it's also the same thing. So it's always a problem of synonym and polysyllab, right? So the terms are not independent. So what we can do is that we can build a middle hidden layer, saying that we have a link between word and topic. We're going to build a probability, conditional probability between them. And then by doing this, in fact, we can you know, tackle the dependency issue. So here is a method. What we can have is that we consider, given a document, there's a fixed number of topics, and for a given document, there's a probability that this document is belong to that topic A. And then from that particular topic, I would also generate terms. You know, for example, the topic will be sports, will be politics, will be entertainment, right? And this given document is likely to belong to one of the categories. And then from that particular category, the terms occurred might be kind of the term distribution might be different. For the sports, you know, prime minister, that term might be higher, whereas you have sports, maybe football might be higher. So you build topic model as opposed to build document model. We're talking about the term distribution. So this is the way to you know, address the dependency of terms, and it's basically called probabilistic latent semantic index. And later on, people developed called the latent derivative allocation as well. So the PRSA is in fact to try to discover the meaning behind the words, as opposed to directly represent the terms. So as I said, it's a hidden layer. Therefore, the topic are not observed. So it's really arguable to talk about when you talk about it's a topic. It can be not be topic. It's just a mixture model, and that's it. And here I'm going to quickly go through it how you can actually do the parameter estimation common with a topic. So remember that this is in fact a mixture model. You have a different topic and you kind of mix it together. We call that we have unilingual representation here. You can replace this probability from given the document, how likely the term will occur in the document, with the PRSA model. And you come with that, and then the parameters is that, so instead of for each of term you have a parameter, you have this two set of parameters. How likely the term, the topic is given that document, and for that topic, how likely the term will generate. And these are the parameters you want to estimate. And what you can do is that you can construct this likelihood estimation from the data you observed, and using EM algorithm to iteratively update that. So I think if you learn, because we have different people have different background here. So if you learn, you are in a machine learning program, so you can, I think, you can easily understand it, go through that. If you're not in machine learning program, it's not required. You understand that. The drawback of PRSA is that the D document is an index into some training set. So it's, there's no sort of notion about the document basically represented by document ID. Therefore, if you have a new document come in, you wouldn't be able to calculate. There's a method to calculate, but it's a bit untrivial to do that because the PRSA doesn't really cover the new document. So that's why Monty with called latent deliberately allocation, which build a top layer, additional top layer there to have the topic distribution. And so here's a sort of a generator process in the LGA. It's like you have first you have a personal distribution to generate the number of words. So the PRSA basically also covers that the document length as well. You first generate number of words. Once you have that, then you generate a topic distribution. And then for each of the words there, you're choosing a topic from the given theta, which is basically the topic distribution. And then you basically generate topic. You first generate topic distribution, generate topic, and then see choosing a word that generate from that particular topic. So instead of you have this topic layer, you have an additional layer which is talking about the topic distribution in certain topic. Therefore, you can able to sort of get a middle problem that for the new document, you'll be able to calculate that document distribution there. Therefore, you'll be able to construct a model for easily construct a model for the new document. That's pretty much it about a topic model. Any questions?
What's beta in previous to last one line?
Previous line?
Yeah, no, in that slide, the previous to last line, there is probability of Wn given theta n, beta. What's beta? Yeah.
Beta is it's beta for it's beta, basically beta is a parameter for that particular if I remember correctly, is parameter for that particular topic.
I think it's another Dirichlet that you choose the distribution of words. It's like alpha.
I think this is a multinomial already, and
Yes.
that bit, this is Dirichlet. Right.
I think there's two different Dirichlets. And you choose a multinomial from each. One for topics, one for words with
Okay,
topics,
then
one for
if
topics
that's the
with
case,
topics.
then this is a multinomial, isn't it? In the term level, and this might be. So the beta is basically the parameter for. Yeah. We talk about how document model is, and you can actually also construct query language, query model as well. And so what you can do is that you have this document model and you have this query model, and then you can calculate care divergency, which is basically measure the similarity between these two distributions. Therefore, you can come up with a score for that. So that's the idea behind this called query document generation. So you have this theta Q, which is a query model, and you have a theta D, which is document model, and then you can calculate care divergency between. So it's like you from the document to build this document model for the query, and then you calculate relevance between. So this is one of extension, and another extension is to relevance. So you can, if you have, so forget about language, but think about this. If I have a set of documents, and they are relevant, if I know they are relevant, and we can actually build so-called relevant language model, which basically those are the relevant documents. I can see how a term generated from that set of language, a set of relevant documents. But it's very difficult to know that set of relevant documents, right? But what you can have is that you can consider query as that set of relevant documents. You can actually help you to estimate, to have initial guess of what the set of relevant document is. So that's the basic idea behind this so-called relevance language model. And you can iteratively actually calculate that, coming with a score function. But you can imagine that it needs a lot of training data before you do that. That's so. This is basically the language model literatures, and I think that it's, you don't need to go through the list. If you're interested in language model, I think this might be the best one to look at. It's simple, and it's actually talking about this. If you read the paper, you can actually understand language model and why linear smoothing works, and how the language model linked to the TF-IDF score that we talked about in Wednesday. I think we still have some time before the break. So what I'm going to do is that we're going to talk about the coursework a bit, and then you will get an idea. And then during the break, you can actually ask a question about it. Okay, so as you know, we have 3 elements in our coursework. And someone asked the percentage right here. I have a definitive answer. So the assignment 1 is about 12%, and the map reduce cloud computing 80%, and the group project about 20%. So the group project, I would hope that each 3 people, 1 group, we're gonna have 1 single mark for the group, and where individual coursework assignments 1 and 2, you will get an individual mark, then put them together, which in total about 40 exams. And the group project, I think I would suggest you to start to think about it now. And already quite a number of people asking about the group project and talking about the project ideas. So what I really want you guys to do is start to think about a topic and find someone who are interested in that, and then define a topic. When you once you make a decision, and send me an email, February 21st. I think about 2 weeks from now, and better title like IRDM, your topics. Otherwise, my mismatch with other emails, I might lose your email. And then what we can do after that is that you might have the final report is in April, so you certainly have about 2 months also, for the group project. In between, in March 22nd, which is our last lecture, I think you're gonna have this presentation, 10 minutes presentation. And for the people already finished off the group project, you can actually present results, and that would be good because that would be help me to understand what you have done, and maybe I'll give you some suggestions in terms of what you want to show in the final report. For the people, they may haven't really finished off, and they may ask for suggestions in the presentation, and then I might be able to give a suggestion in terms of what you can do about this the group project. And for the assignment, the deadline is also here, and it's roughly I think two weeks from now, and also I think at the same time we're gonna, before the deadline of the assignment 1, we're gonna release assignment 2, so you also have about 2 or 3 weeks to finish off that. So any question about deadlines? No? Okay. So this is a slightly different with what we actually proposed last year. Because last year we have 1 fixed deadline for everybody and for all the 3 assignments. But it turned out that it's not really good because we are very I'm a bit flexible because I put this deadline almost like 2 weeks after last lecture. But everybody finish off everything like one week before that. So really got a lot of pressure on you guys. So not for me, on you guys. So I think it would be nice, good to have a separate deadline so that you would be able to properly arrange your work coursework. I understand you have other coursework as well. So let's try this to see whether it works. Which one you prefer?
I think this looks good.
Any questions? Okay. About the group project, and do you think what would be the best way? One way is I'm gonna randomly assign a group. That's one way. Another way is that you find your group member. In the last few years, we ask you guys to find a group member, and but always had 1 or 2 people in the end who were able to find someone work together. Therefore, did this group project individually. So as alone. So it didn't really work out in most of situations. So what I really encourage you guys to start to talk now, talk about project, try to convince other people this is a good project, go. And then if you worry about data set or something, talk to me. You know, I'm able to find data set for you. So I don't want to really you guys to crawl the data, start from scratch. Sometimes it's really time consuming. So it would be good to have some data and work out using some existing data set is also good. Or maybe using it as an opportunity to try your thesis project. So you might have some idea about your thesis project, and then you can using this as an opportunity to conduct early study about it. I mean, I'm open-minded. Whatever project you can think of, or as long as has some relevancy with the data mining and IR. I know someone has a completely last year gave a completely different topic, which obviously I call Mark like that. But you know, for the topic, I'm gonna have few examples, suggestions about that later. Yeah.
I was just wondering how they're going to be assessed. Are they going to be assessed like statistically on an error measure, or will you get kudos for complexity? Even if it doesn't work as well as a simple method.
Okay. Well, you mean the evaluation?
Yeah.
Yeah. Well, I will talk about it later. But the short answer is that as long as you have some analysis, so this analysis could be mathematical analysis, could be the evaluation. Yeah. So assignment 1 is a text retrieval. If you go to the Moodle, there's a step-by-step guide and the task description. So I think Mark did a very nice job to come up with this notes. So briefly to talk about the some instruction about the track, and then talk about collections and where you can get topics and also get these relevant judgments and what format that is. And then you can download this the package which contains the source code and data set, and then a very brief instruction about this, how you can make it work, even though you probably never used Java before. And you again, from this instruction, you might able to, I'm not saying 100% sure, but you might able to run the code and come up with your initial result. If you don't, send me email or send Mark email. So it also have this how you can make it work in Windows. If you are in Mac, sorry about it. Then there's assignment here, which basically talk about the task you're gonna do and what result you'll be able to produce. That's it. So I'm not. When Mark comes, I'm gonna ask him to give a brief introduction about assignment 1. But for assignment 2 is MapReduce, and because the parallel computing, cloud computing become very critical when we do large-scale data analysis. So this assignment 2 basically is designed for that. We're going to introduce that after reading week. Make sure you won't be overloaded with by the work provided us. And we're gonna give you Amazon coupon, which is worth $100. So, but still, when you use it, still be careful. You have to kill the jobs when you don't use it. Because some students last year came to me, I already used up $100 US, and so I gave him about 3 more coupons. Well, he used it up again, so there's something wrong there. So I found out that he didn't really kill the cost.
Was it worth it in the end? Was his result good?
What do you mean?
It was a bad joke.
For that guy, it didn't. Yeah, the group project. So you can use in Java, but other language possible. You can use MATLAB, whatever you're doing. And the assessment, try to exam weight, clear description of your system, motivation of design choices. So what I say is that you got the data, do some analysis. What I need is the analysis, which is very important. I don't really care what sort of evaluation measurement you're going to come in with, what problem you want to address. But if you have sensible analysis of data, I think that will be good. So here's some examples that previous student did. One thing you can build this distributed web search. We know we have learned retrieval models, right? We're using this the Panda software package, and we also learned about reduce. Now the question is, can we build a modern distributed index coming with a distributed web search? So you able to using like some CPUs, either using Amazon or the one we provided to come in with infrastructure, and also putting one with the search engine to see how it goes. Yeah. Another is that you can come in with a single search engine, and then limited to, let's say, UCL web page. Can you build a web search for UCL? And hopefully to see whether the search engine is better than the existing ones. The user, I know user got the third-party search engine. Well, it's better now. It used to be very bad, but now it's better. But if we learn, what would be the best retrieval models here. So you certainly got opportunity to improve that. We'll do a better job than theirs. But I think what they do is that they're using some of the open source software package for ranking. So you learn a lot of advanced ones. I wouldn't say advanced ones. You learn some of the better ones. So try internet to see whether you could able to have anything better than that. If you are machine learning background, right, and you're not say I'm not going to build a system. What I'm interested in is in algorithm. That's okay. So you would one way is say, because we already have this set up. We have evaluation data set, and therefore you could able to build some machine learning, a little bit of learning in retrieval model, right? You can build this, let's say for example, LDA, PRSA, and then try to see whether it works or not. This is some ideas, but you can come in with other technique as well. So what I try to say here is that you don't not necessarily build a system, but I'm going to concentrate on the specific algorithm, specific model. Can I do something better than that? Recommender system, which we haven't talked about yet. So here is that you could do IR, you could also do data mining. So here example, you can build a recommender system. So here you can build a system yourself by using some new data, or specifically working on a model, a mathematical algorithm. It's also fun. It's quite interesting. Last year, people were not really familiar with Java. They end up doing recommender system because the data is very clean, easy to manipulate in the in MATLAB. So you can use one of the data. We realize the data is very small, about 1,000 users, 1,000 items as well. So it's very easy for you to try some mathematical models and make prediction. Since we talk about visualization in our second lecture, so I think you could think about able to using some visualization technology to visualize user taste, and if you're interested in that. So these are the possible ideas, and also I offer these two projects. If you want to say I want to combine this with my thesis project, so one thing you can do is that again, this example is some of my students started working on this the idea about build social networks on top of search engine. So if you are interested in that, you can talk to us. We can ask you to join our group. McGill, who's yeah, so because he's one working on that. So if you are interested in that topic, talk to him. Then you might. I'm not sure whether you're gonna choose this as a group project or you wanna do something different.
Not sure yet.
All right. Yeah, I'm not sure. But anyway, if you're interested in this project, and always talk to him. He probably will be able to show you a demo. Not reliable one, right? Another project. Is it Shah here? No. So this is another a project with two of students of mine, and the idea was that Google is good to retrieve relevant documents, but in fact the internet can do something different. For example, can we turning Google into an online dictionary, writing assistant tools, help us think about the internet? There are a lot of articles there, right? A lot of literatures. They give a very good example about English writing. But if you look at online dictionary, the dictionary itself is the example there is rather static. The question is whether we would be able to using the sentence in the internet as an example in the dictionary. So this is the idea we came up. But if you think that way, a lot of things can be done. A lot of possible application on top of that. And yeah, that's pretty much it is. Yeah, if you have any questions, you can always talk to me during the break. Okay, let's have 15 minutes break.
Out of interest, can I ask who is still looking for a group?